Okay, guys, so this is, um, I'm recording this on May 4th. And the reason I'm doing this recording is I realized my lecture description of how we're going to do the presentation was pretty confusing. So I'm going to do it again. Hopefully, this time it'll make a little bit more sense. So first, let me tell you the problem I'm running into with the presentation. When we started the semester, I was hoping that having this presentation assignment would allow you guys to link the stuff we're trying to learn in the class with a real chip, a real product that you could look at and have a better feel for how these things translate to an actual product. So the four aspects that I think are important in VLSI design are cost and performance, power consumption, and reliability. Or robust design, however way you'd like to call this one. So something that works in the real world without breaking down. And what I was trying to do when we would touch different aspects of the VLSI technology is to see how things are related to each other and what the metrics may be. For example, in performance, I was talking about clock rate or clock frequency on your chip being an important metric of the design performance, how fast you can run. And then we tried to look at how this is related. There's a trade-off between the clock frequency and the power consumption, so which was CV squared F, okay, with F being the frequency component. And similar thing with robustness, reliability, we looked at V in versus V out, for example, for an inverter, and having noise margins around this, and how the higher the supply voltage, the higher our noise margin, the more you can the higher the voltage noise peaks that you can ignore, the higher the supply is. But then the supply is also a trade-off with the power consumption. Things like that. Now the cost was NRE and cost of goods sold, and that was dependent on the area, and we talked about that, how that was related to some of these. Now what I was hoping for the presentation was that we would be able to, for each one of your chips, to be able to do some quantitative analysis in regards to all four of these metrics. The problem that I see is that the only quadrant here that seems like it's really even possible to do any kind of quantitative analysis is this cost quadrant. At least there we can estimate chip size, we can try to guess or find out what process technology the chip is in, what kind of package, basically make some educated guesses and come up with this metrics. Now, the other ones though, I think it's, looking at it, I think it's gonna be very difficult for you to come up with any kind of quantitative information here without really, really, really digging in and doing just a huge amount of work on the presentation, far beyond what I wanted to have you guys have to do. So for that reason, I've changed the format of the presentation to make it only 2 to 3 slides long. So this is for the total. And the idea is that you would have some idea on the cost calculations. That would be one of your slides. So slide 1 would be the cost calculations. And you would bring that, slide 1, you would bring that to either our May 7th or May 13th meetings. So I would be meeting with you individually, and we would look at that, make sure things are okay, and then try to come up with some business reason or look at like what you could put into slides 2 and 3 in regards to some of these other metrics. Okay, and we'll see how successful that is doing it together. The thing I'm really looking for isn't how close to reality this is, but really the thinking behind it, so that we both go through and make sure, that, it's a learning exercise for you guys. So can we think through how changing the cost or looking at the cost parameters, what that'll lead to in terms of these other things, and seeing if it translates to some idea of a business model. Okay, so what I wanted to do then, so with that background, is to talk a little bit about what I was hoping you guys would be able to show up with on May 7th or May 13th in your time slot. What kind of calculations you could do there. Okay, so let me go. I did it briefly. I don't know if it made sense, so let me do it again. So we basically started with the idea that there was a 14 nanometer chip from AMD, and we were thinking of, what would we do with this? So one option was we ported from 14 nanometer to another process, so to see if we can get cost reduction. Okay, so what you do it is, if you take this from 14 nanometers to a 10 nanometer process, you would end up with a chip size shrink, and that, first let's see if that'll give a lower cost, because the chip size will shrink but the wafer price goes up. So let's see what that does. Okay, so if you're going from a 14 nanometer to a 10 nanometer process, this is, you could think of it as, if you're trying to, we gotta first thing we gotta do is estimate what is the size shrink of the die. So let's say the transistors are shrinking in from 14 nanometers to 10 nanometers on a side. Okay, so the question is, if they're going down by 14 nanometers on a side, going from 14 nanometers to 10 nanometers, what does that mean to the area? So let's just look at it. If you got to remember that it's area, not just a single dimension. So, 14 squared is 196 and 10 squared is 100. So if you go from one to the other, from 14 nanometer to 10 nanometer, you would, expect that your silicon area might shrink by 2x. Okay, so you're going from that to that. Okay, so but let's say, it's not always, I think it's always good to assume you're not going to do as good as that. There might be some parts in your chip, like, we talked about the peripheral pads, things like that, that may not be shrinkable because they have to be a certain size to fit in the package, etc. So let's say we say the silicon area in 10 nanometers is going to be 60% of silicon area in 14 nanometer process. Okay, so let's work with that. Okay, so first, let's come up with an idea about what the silicon area is, an estimate of what the silicon area is for this chip. This was ended up being a AMD so-called Zen processor. You guys can try to look this up. But the team that was working on it came up with an estimate of $200 for the price of this part. So, and then looking at AMD, we saw that their average margins at AMD was something like 50%, which is a good guess for any American company that's doing fairly well. Okay, this is this average margin. You can also, some people call it, there's different words for the same thing, I think. There's also, called gross profit margin, that kind of thing. So this is the first place where it's easy to go wrong. So let me give you the equation for this. So, the gross profit, you guys can look this up too on Wikipedia or whatever, is the sales price minus the cost of goods sold. And in this case, we're trying to figure that out. We're trying to go backwards from the $200, which is the sales price, and we want to see what the cost is. Okay, so sales price minus cost of goods sold over the sales price times 100, because gross profit is given in percentage. Okay, so let's say in this particular case, we say gross profit is 50% is, we have the sales price as a approximation minus cost of goods sold over the sales price, $200 times 100. Okay, and that gives you $100 for the cost of goods sold, which is the cost of making, the incremental cost of making this product. Okay, if I use the examples, if this had a 70% margin, so this is what we're assuming, but if the margin was 70%, this would end up being 200 minus cost of goods sold over $200 times 100, and the COGS in this case would end up being $60. Okay, so the reason why this is a little bit confusing is because we're going backwards from what we from the sales price and the expected margin to a cost of goods sold. So what some people do when you say, oh, you got a 70% margin, you think that you're, somehow 70% of, well, anyway, like it's easy to go wrong with the calculations. So you might think that, if your cost of goods sold is $100, you can make 50% profit on that. That's not how it works. You got to go by this equation. So a lot of people get confused about this. Anyway, long story short, I don't want to confuse you in addition, but just follow this equation and you work backwards to get your cost of goods sold. So we're gonna assume we're here for or $100. So cost of goods sold in 14 nanometer process is $100. Okay, and then this is gonna have three components. It's gonna have more than three, but three major components. The cost of the silicon, the package cost, and the test costs. And I just made some assumptions here. I said, look, the package is, on the package is a high pin count. It's a processor. It's got a lot of pins coming out of it. It's, pretty high power consumption. I think it's in the tens of watts. So you need a relatively large package. It's probably a plastic package. It's probably not, it's not a military grade part, etc. So it's going to be probably, my estimate, tens of dollars. So I said, okay, let's say the package cost will be around $20. So, and if I was going to make this presentation, I would put some assumptions there. So high pin count, high power dissipation, but not military or slow or like exotic. Okay. Now the test cost, I think a good estimate is that I put in $20 for a test cost. Again, it's a big chip. And what my estimation was that typically test systems, the price per test system is $150 per hour. And I said, okay, it would take about 10 minutes to test this part. And that's what you should put in, something like that. So if it's if you're talking about a really small microprocessor for, a Raspberry Pi or something, it's not going to take you 10 minutes to test that necessarily. It could be significantly less. So, and the package may be a lot less expensive if it's a low pin count device, low power consumption, etc. So anyhow, so $20 for this guy, $20 for this guy. It ends up being a, let's see, the total cost is $100, cost of goods sold. So it ended up being $60 for estimate for the silicon price, silicon cost. Okay. So now what do we do to that? Well, first let's see what the wafer price is we're expecting. So I sent this thing out to you guys, I think, a while back, but it's sort of gives you some idea of pricing. This is estimates of pricing at different wafer nodes. So if I look at this, I see that as 16 or 12 nanometers, so 14 nanometers in the middle there. So I'm going to use the same number, is $3,984. Okay, this is this middle guy. So let's say approximately $4,000 per wafer. So I'm going to assume at 14 nanometers, we're going to have to pay $4,000 per wafer. Okay, and then let's see. So that would means that they are probably getting, so number of good die per wafer is probably $4,000 per wafer divided by $60. So it's, approximately 66 die per wafer is probably what they're getting. Now I can take this to my, to another website that I sent you guys the link to, which is a place to calculate the die sort of the number of good die that you would get for per wafer. And the idea here is you can work backwards from there to come up with your die size. So I played around with this for a bit. So one thing to remember, by the way, is make sure you put in that you're working in a 300 millimeter wafer, which is a 12-inch process. Almost all the parts you guys came up with are in, I think all of them, it's a good assumption that they're going to be in a 300 millimeter, wafer process. So I I'm looking at this, can't zoom in here, but if you guys see in green here in this graph, it gives you the good dies is 70. The total die is 112 at the bottom, but there's a yield that this is estimating. So this is giving us a number of good dies of 70, given this die size, 22 millimeters. Okay, so that's pretty close. We were estimating 66. So basically this says that my estimate is that at 14 nanometer die size, so silicon die size is 22 by 22 millimeters. I'm estimating up here, I made the assumption that basically the area of my 10 nanometer design, if I did that design port, was going to be 60% of whatever I have with this. So this area, so this goes to area is 22 squared is 484 millimeters squared. And so at area at 14 nanometers, so area, if I do a port to 10 nanometers, it's going to be 60% of that. And that's going to give 290 millimeters squared. Or a die size of 17 millimeters by 17 millimeters in 10 nanometers. Okay, so I will stick this in here. And we get a number of good die of 140, as you guys can see. So this gives 140 good die per wafer in 10 nanometer process. So, and then if you look it up, what the wafer pricing is for 10 nanometer, it's looks like about $6,000 in wafer pricing. So wafer price is $6,000 in 10 nanometers. So by the way, notice that the reason we're going through this, like we could have just said, we could go, we've got 66 die per wafer in the 14 nanometer process. I'm going to shrink by 60%. And so that's, I could have just used that ratio to get the new ratio, the new number of die per wafer in a 10 nanometer process. The reason we didn't do that is because As you guys remember, when you shrink when your die get smaller, your yield will also go up. So it's not as straightforward as just doing a ratio. You have to plug it into something like this. You get the new die size. Actually, as the die size shrinks, your yield will actually go up. So you'll do somewhat better. So notice that although we only assumed that the die size didn't even go down by a factor of 2. We assumed that it only did the new die size wasn't even 50% of the old one. It was 60%. But even with that, notice that we more than doubled the number of good die in the new design than the old one, although we didn't shrink it by 50%, but the yield went up. So that actually, even though we didn't go to half the area, we got more than double the number of die per wafer. Okay, so that's like the pricing. That's what happens when the dies shrink, which is great. Now the wafer price, we more than doubled the number of die per wafer. The wafer price went from $4,000 to $6,000. So the price is going to go down. So now the cost of silicon in 10 nanometers is going to be $6,000 per wafer divided by 150 good die. And that is 140 good die, I'm sorry. That's $42 in new silicon cost. Okay, so we went from $60 to $42 in silicon cost. And I don't think too much is gonna change in the packaging or the testing. It's the same complexity part. So I think, the package cost and the test costs aren't really gonna change. So if we do this shrink, we're gonna make an extra $18. Let's say if we sell it for the same amount. So we still sale price stays at. So if sale price stays at $200 per part, our total cost of goods sold went down by $18. So that's how much extra we'd make per part. So extra profit per part is $18 under these assumptions. Okay, so now it cost us, unfortunately, a bunch of money to make this part, and this is going to slide deck 2, slide 4. I had some estimates of the non-recurring engineering cost. That's how much it costs to design and create this part. And so let's see what that looks like. So in the 10 nanometer process, that the estimate for that is 174 million, 774.4. So that's 175 million. So let's say that was our NRE. So now we want to see how long it'll take us to get our NRE back. So let's say NRE is $175 million. Okay, so let's say we want to make our cost back, but we also need to make some profit. I mean, it's $175 million. You don't want to just spend that and don't make anything on top of it. So let's say we want to look at how long it would take us, or how many more parts you would need to sell to make up 2 times the NRE, say, which is $350 million. So we divide, so number of parts, number of additional parts. Let's say you were the same company and you were thinking of doing the shrink to, increase your profits. So the number of additional parts to sell to get NRE back plus profit, that would be $350 million divided by $18 per part. And that is going to be that's about 20 million parts. So basically you have to you have to sell 20 million additional parts compared to your previous sales projections to make it worthwhile to do this 14 nanometer to 10 nanometer shrink. Okay, so this was the cost calculation. Now what I'd like for you guys to come to this or next Friday's meeting, depending on which one is signed up for, is this calculation. And from here, together, we're going to have to come up with a story about, what will allow or what will be enticing in your new design to sell 20 million additional parts. First of all is the the market for your part. Is it big enough to sell 20 million parts? 20 million parts is a lot. So in this particular case, it's an AMD processor. So yeah, I would guess, you'd sell millions of these. It's going into PCs and those kind of things. But if you have a specialty part, like something in a much more focused, it's more specialty part, you're going to sell fewer of those. So we're going to have to come up with, hey, is there a business case to be made for this to port this part? For example, if your power consumption goes down, or say your performance goes up, or something else happens, would the market find that enticing enough for you to make this investment or not? Or it just doesn't make sense? All those are good answers. So those are the ones, that I'd like to brainstorm with you guys in our 20 minutes together to see what we can come up with. And again, there's no winning or losing here. The conclusion just may be that, excuse me, that it's not worthwhile doing this port to a tighter process. But that's also part of our learning here, is trying to basically look through this and trying to figure out, what the cost differences are, and does it make sense in terms of some kind of an additional improvement to make this move. Anyway, I hope that was a little bit more clear than my earlier my Zoom presentation to you guys. And anyhow, we'll be talking, and looking forward to talking about all this stuff in more detail with you guys in the next couple of Fridays. Take care.